Okay. Yeah. Thank you for introduction. And yeah, thank you for organizing this nice school and kind invitation. I'm Masaki Oshikawa from ISSB University of Tokyo. So I think this is maybe my second time visiting Rice University, maybe third time. Sorry, I forgot. But at least this should be the first time for me to come here with my bicycle, which is here. So I'm very happy. Although so far I have just commuted from hotel to here, so just a few miles. But okay, so I was asked to give this title lecture, Correlation Physics and Introduction. But I have to say I'm not really expert on so-called correlation physics. I guess you should ask Chiba for real correlation physics. But okay, so since I got this opportunity, let me give some very biased introduction. So, and correlation physics is very vast subject, so it would take one semester or two to give some reasonable introduction. So, please allow me to give very some biased or narrow kind of introduction. Okay, so so what is correlation physics? Okay, maybe I should. Just move. How do I? Okay, yeah. Yeah. So so actually I think it's kind of word which is often used in condensed matter physics without clear definition, at least in my understanding. Because when people say correlated systems or strongly correlated system, it usually means electron system where interaction is strong or interaction plays a significant role or essential role. But I don't think people really quantify how much correlation this electron system have. But when you have strong interaction, and if it is important, people say it's strongly correlated physics. And actually, it's kind of buzzword. At least it used to be. And these days, maybe people talk about the same thing using entanglement instead of strongly correlated. But still, correlation is, of course, very important concept. And strongly correlated electron system or strongly interacting electron system is very interesting subject, which gives us many intriguing phenomena. But I want to emphasize that, yeah, as a previous speaker discussed mostly topology of free electrons, even free particles, which is often called weakly correlated system or something, but even free particles, non-interacting particles, are intrinsically correlated because of the quantum nature or quantum statistics. Actually, we can try to quantify the correlation, but usually correlation can be measured in terms of correlation function. But you can choose different physical quantities. So if you pick up different physical quantities, then correlation function behaves differently. So you can ask what is more universal measure of correlation, which is independent of the set of the physical quantities you choose. And one answer from information theory is so-called mutual information. For example, if you have a big system and divide the entire system into two parts, A and B, and you can define so-called mutual information. Okay, so this lecture is not really about information theory, so I'm not going into detail, but maybe you have already heard this word somewhere. So mutual information roughly means that if you measure all the possible physical quantities in region A, let's say, and then you can infer information on region B. So this is basically mutual information. And at least in the special case of the pure quantum state, for example, the ground state of certain Hamiltonian, then this mutual information is actually identical to maybe better known quantity entanglement entropy between this entanglement entropy of bipartition. That is, you again divide the entire system into subsystem A and B, and total density matrix for entire system is just a projection to the ground state or pure state psi. But if you take a partial trace over system B, then you can obtain the reduced density matrix rho A. And now, so this meaning of rho A is if you can only measure physical quantities defined on region A, then this reduced density matrix rho A contains all the information. You can obtain the expectation value of any physical operator defined in region A. So rho A encodes all the information you can measure in region A. And even though the entire system belongs to the pure quantum state, if you only look at region A, you cannot distinguish this with the so-called mixed state. So rho A can be regarded as a kind of mixed state density matrix. So you can compute the entropy in usual way. And this is nothing but so-called entanglement entropy. And as I mentioned, in this special case, this is also identical to mutual information. So this quantity tells us how much information you can infer about the other part of the system, region B, from all the possible measurement in region. And this entanglement entropy has been studied recently by many people. And it's recognized that, okay, so if you pick up really random pure state, then the entanglement entropy follows so-called volume law that is roughly proportional to the volume of the subregion A. But for ground state of generic Hamiltonian with short-range interaction, we usually find so-called area law, that is entanglement entropy is proportional to the area of the boundary between subregions A and B. So if the linear system size of this entire system is L, then this area of the boundary is basically proportional to the L to the power of D minus 1. So in 3D system, the boundary is area, so L square. But if you have two-dimensional system, the boundary is curve, so it's L linear. But this is also interesting result. For the ground state of non-interacting Fermi gas, so-called generic Fermi gas, not Dirac or something. When you have Fermi surface, then the entanglement entropy is actually almost like a area law, L to the power of D minus 1, but there is a logarithmic correction multiplied by log L. So in fact, the ground state of non-interacting Fermi gas has a somewhat larger entanglement entropy than the generic quantum system, quantum many-body system, like a so-called strongly correlated system. So in a sense, free fermions are more entangled or more correlated, at least in this measure. So I think we should be careful using word correlation, but still, okay, conventionally, when we talk about a strongly correlated system, it usually means a system with strong interaction. Okay. So as I mentioned, even free particles have intrinsic correlation because of the quantum statistics. And these days, so-called AMO physics, atomic, molecular, and optical physics became very active. And we can import some concepts from condensed matter or solid state physics to AMO physics and vice versa. So yeah, it has become very fruitful area. So sometimes I learn about the very basic of AMO physics. And I don't know, maybe some of you are from that field, then what I'm going to tell you for a few minutes are really basic. But for condensed matter physics people, maybe this is new. So I want to discuss this for a few minutes because I only got to know this very basic phenomenon uh, rather recently. So if you come from magnetism, superconductivity, you don't learn much about this stuff. So let me uh, introduce some interesting effect of quantum statistics. So in optics in particular, they often use uh, so-called beam splitter that is originally developed for optics. So it's like a half mirror. So if you shoot light, then this mirror transmits 50% of light and reflects 50% of light, roughly speaking. So in classical physics, light is electromagnetic wave. So this kind of half transmission, half reflection is kind of easy to understand. But in quantum mechanics, everything also behaves as a particle. So even the light is a collection of photon. So you can imagine shooting the single photon to this beam splitter. Then this photon is transmitted with probability 1/2 and reflected by probability 1/2. Then to this beam splitter, you can shoot photon or some particle from left or down. And then these photons or particles may be either reflected or transmitted. So there are two output channels. So this kind of station can be formulated in terms of S matrix. That is, I have two output channel, this red one. So let us write up psi 1, psi 2. These are quantum amplitude of outgoing channel. And this psi 1, psi 2 in is the two component of some particle coming in. So it's a two component vector or wave function. And as usual, this outgoing wave is related to incoming wave by so-called S matrix, 2 by 2 matrix. And for example, if I only shoot particle from channel 1, then this psi 1 is 1 and psi 2 is 0 in incoming channel. And this S matrix is this 2 by 2 matrix. So you can write down S11, S12, S21, S22. And if you multiply, of course, you get S11 and S21 as outgoing wave. And I want to consider so-called 50-50 splitter. So the particle is transmitted or reflected with probability 1/2. That means that this absolute value of S11 and S21 are both 1 over square root 2. And similarly, if you consider incoming particle from channel 2, and if you demand 50-50 splitter, then the other elements must have also absolute value 1 over square root 1 over 2. Okay. Then I can, because everything has, every element has the same absolute value, I can parameterize this S matrix like this. Some overall factor, phase factor over square root 2. And I just fixed this element as 1 because I have phase factor here. Okay. I can put this here also, if you like. And then other three components can be also parameterized as phase factor. Then this alpha, beta, gamma, theta look like arbitrary, but of course it's not really arbitrary because S matrix comes from unitary time evolution of quantum mechanics. So S matrix must be unitary. So S times S dagger is 1. And if you require this S matrix to be unitary, you can obtain this equation, which implies that actually this third element, E to I gamma, must be equal to minus of exponential I times alpha plus beta. Okay, so the S matrix should look like this. Alpha, beta, theta are still arbitrary, but something like this. Oops. And once you obtain the S matrix, so if you have single particle, everything can be described by S matrix. But I want to discuss a multi-particle, actually, at least two particle physics. Then it's convenient to introduce the creation operator for of particle. But so if you create the particle in incoming channel J is 1 or 2, then you apply time evolution. And as a result of time evolution, you must reproduce the same scattering. So you must find that this unitary transformation of the incoming creation operator by time evolution operator must be given by this S matrix times the outgoing channel creation operator. So if you use this equation, then for single particle physics, you can reproduce the previous result. But now I want to shoot two particles at the same time from channel 1 and channel 2. In this case, incoming state, initial state is given by creating particles both in channel 1 and channel 2. And this zero ket is a vacuum. So you create particle in both channels. And then we want to know what is the outgoing state as a result of time evolution. So I just follow the basic principle. So I apply this unitary time evolution operator to the in state or initial state. So this must be the answer, out state. But this initial state was C dagger times vacuum. Okay. But now we can insert this U dagger and U dagger U because U is unitary, so you can insert U dagger U dagger U anywhere. And U dagger time evolution applied to vacuum is just a vacuum. So you can also insert U dagger here. So then this is nothing but a unitary transformation of C dagger 1 and C dagger 2, which I fixed in the previous slide. So I can write this unitary transformation in terms of S matrix. And if I write down every component, the result looks like this. This is just a S matrix is 2 by 2, so you can work it out easily. Then I get a four state, C dagger 1, C dagger 1, and C dagger 2, C dagger 2, and C dagger 1, C dagger 2, and C dagger 2, C dagger 1. Okay, so if the system were classical, then these four states are different states because you can distinguish two particles. But the quantum mechanical particles are indistinguishable. So as you know, this C dagger 1, C dagger 2, and C dagger 2, C dagger 1 applied to vacuum are just states with one particle in channel 1 and another particle in channel 2. So they are the same identical state. You cannot distinguish this. So you have to put them together. And in fact, if you are familiar with the second quantization, you can change the order. And let's consider the case, these particles are bosons, which is a case in case of light, because photons are bosons. So I had this C dagger 1, C dagger 2 applied to vacuum, and C dagger 2, C dagger 1 applied to vacuum. But for bosonic particles, you can exchange the order of this creation operator freely without any phase factor. So you can change this order of creation operators, then you get the same state, C dagger 1, C dagger 2. And the coefficient is S11, S22 plus S12, S21. Okay, some coefficient. But I have already fixed the form of the S matrix explicitly. So I can actually calculate this S11, S22 plus S12, S21. Then you can do this calculation. So phase factor I theta got squared, but 1 times this minus e to I alpha beta, and plus exponential I alpha times exponential I beta. So if you look at this carefully, actually, because of this minus sign, they completely cancel for any choice of alpha, beta, or theta. So, and this form was enforced by unitarity. So as long as S matrix is unitary, so this combination actually vanishes. So which means that you have 50-50 beam splitter, and then you shoot two bosons, let's say photon, at the same time from two channels. Then these two photons cannot end up in different channels because this amplitude is zero. So what they can do is when I shoot two particles from two different channels at the same time, then with 50% probability, the two particles comes to the same channel, one. And the other possibility, one half, 50% is two particles also go out on the same channel, channel 2. But you cannot have one particle to channel 1 and one particle to channel 2, which should happen if particles are classical, but for bosons, somehow it cannot happen. And this is, in this field, it's very famous effect called Hong-O-Mantel effect, originally discovered for photons. But now people are doing this kind of experiment using atoms, either fermions or bosons. Colloquially, this kind of phenomena can be called as bunching of bosons because multiple bosons tend to occupy the same state or take the same position or take a same state. So this is called bunching. And this is somewhat similar to Bose-Einstein condensation we are probably more familiar with. Of course, they are different because Bose-Einstein condensation is about equilibrium, some thermodynamic equilibrium, and this effect is not in the equilibrium, but rather as a result of the quantum dynamical process. So they are not the same, but still, it's kind of similar in flavor because it shows that the bosons tend to, group together and occupy the same state. And then we can ask same question for fermions. Although for fermions, the answer is kind of obvious without doing any calculation because if those fermions don't have any spin or any internal degree of freedom, then if you shoot two fermions at the same time from two channels, then fermions obey Pauli principle. So no two fermions can occupy the really identical state. So you cannot have two fermions coming to channel 1 or channel 2. So the only option is one fermion goes out to channel 1 and the other fermion goes out to channel 2. So it's kind of obvious, but in terms of calculation, we can see the difference. So first, C dagger square is 0 for fermions, which means that you cannot put two fermions in outgoing channel 1 or either 2. But this C dagger 1, C dagger 2 vacuum term was important. So up to this point, I didn't change the ordering. So the calculation was same between boson and fermion. But for fermion, when you exchange the order of this creation operator, you get a minus sign. So now the coefficient of this S212, S21 get a minus sign. And then C dagger 1, C dagger 2 vacuum. So this is a physical state which corresponds to one outgoing particle in channel 1 and the other outgoing particle in channel 2. But the coefficient is now different. And if you look at this formula, this is 2 by 2 matrix, S matrix. And this expression is nothing but determinant of S. So for unitary matrix S, determinant S is always non-zero. And its absolute value must be 1 because of the unitarity. So that means that by 100% probability, these two particles coming in from different channels must go out to different channels. Of course, that was obvious from Pauli principle, but still, you can check the conservation of probability, which is kind of nice. So this kind of behavior is often called anti-bunching because fermions tend to, take different state. And in this case, it's our only option. So it's kind of obvious, but still, we can see the clear difference between bosons and fermions. Okay, so far, some interesting example in AMO physics, but I guess I have to talk about condensed matter physics. Otherwise, I would be kicked out from this room. So let me discuss magnetism, which is one of the most important phenomena in condensed matter physics. So most of the materials have zero magnetization when you don't apply magnetic field. But if you apply magnetic field, this magnetic field can induce magnetic moment. And for weak enough magnetic field, usually this relation can be regarded as linear. So magnetic moment is linearly induced by the applied magnetic field. And most natural case is this susceptibility chi. So this proportionality coefficient is nothing but the magnetic susceptibility. And maybe most natural case is this susceptibility chi is positive, which is called paramagnetism. But some quantum system can exhibit negative magnetic susceptibility, which is called diamagnetism. And in fact, it's a common problem we solve in undergraduate or graduate StatMech programs to calculate the magnetic susceptibility in free electron gas. And there are two components. One coming from the spin degree of freedom, which is Pauli paramagnetism, which is perhaps easier to calculate. But magnetism coming from orbital magnetic moment is a bit more challenging to calculate. But this is called Landau diamagnetism. And for free Fermi gas, there is a famous relation between Landau diamagnetism and Pauli paramagnetism. But anyway, so in free electron gas, you can have a paramagnetism and diamagnetism, but there is no spontaneously generated magnetic moment at zero magnetic field. So, but ferromagnetism, which probably we have been familiar since kindergarten or elementary school, because we usually have some magnet as a toy and we can pick up some nail or a clip or whatever. So we have been playing with this magnet. And in real life, this magnet can be useful for many purposes. So although when I study magnetic system, it's mostly anti-ferromagnetism. I have to admit that probably ferromagnetism is more practical useful. But on the other hand, at the same time, it's kind of difficult to realize ferromagnetism. Of course, we do have ferromagnets, so we can use putting something on the refrigerator and so on. But actually, people had to find some special magnetism, special materials which can exhibit ferromagnetism. So it actually occurs in a relatively small number of materials within a vast, variety of different materials. And this difficulty is actually linked to the fermionic nature of electron because it's usually electron spin which contribute to ferromagnetism. And in fact, we will see that if you have non-interacting electron system, free electron system, then you cannot have ferromagnetism. And this is related to the example I discussed because fermions tend to, anti-bunching. So they cannot, get together to occupy the same state because it would be against the Fermi statistics or Pauli principle. Especially because ferromagnetism means roughly means that all the spins should take the same spin state. But electrons are fermions, so they don't want to do that. So if you want to realize ferromagnetic material, permanent magnet, somehow you have to force electrons to take the same spin state. But it's kind of difficult because it's basically against the Fermi statistics of electrons. And yeah, we can easily see that because yeah, as previous speaker discussed, if you have free electron system, first you want to obtain the band structure. So band structure means that for each wave number, there is a certain energy state, and you can draw the dispersion and so on. Then in the ground state, you want to minimize the energy, which means that you want to feel the lowest energy state first. You put upspin electron first, but the same low energy state is still empty for downspin electron. Although you cannot put extra upspin electron to the same lowest energy state. So you want to put the downspin electron to the same lowest energy state. Then next, you have more electrons. So you need to put those electrons to those orbitals or single particle, single electron eigenstates. So the second lowest level, you put up electron. Then you cannot add another up spin electron to the same state again. So you need to put the down spin electron and so on. So you feel the lowest energy states by up spin electron and down spin electron, up spin, down spin, up spin, down spin. So the ground state of the free Fermi non-interacting electron system is always like this, basically. So the upspin and downspin cancels. So the entire system is non-magnetic. So in this way, you cannot obtain a ferromagnetic state. So that's a challenge to realize the ferromagnetism. So that means that you need, at least you need some interaction to realize ferromagnetism. So the next question is, can we really realize ferromagnetism by introducing interaction? And the answer seems to be yes, at least from the simple mean field picture. So of course, real material are very complicated, but we can consider a very simplified model of interacting electrons. And one of the characteristic models is so-called Hubbard model. The Hamiltonian looks like this. So you consider some lattice, like a square lattice, a cubic lattice, or whatever. And each side can be occupied by electron, either up spin electron or down spin electron. And then if electron is occupying one side, that electron can hop to the nearest neighbor side by this hopping term. So if you have just this first term in the Hamiltonian, it's called a tight binding model for non-interacting electrons. But you can introduce this so-called on-site Hubbard interaction, which is a repulsive interaction between upspin electron and downspin electron on the same side. So again, you can include the interaction between neighboring sides and so on, but this is a simplest form. In which only the upspin electron and downspin electron on the same side, at the same site, interact with each other. Okay. So this is a Hamiltonian. And since basically the electron interaction is repulsive because it basically comes from Coulomb interaction, let's consider the repulsive case positive U. Although sometimes we also consider negative attractive interaction, but here we consider the repulsive interaction. Then, so this term is represent interaction. So once we have this interaction term, generally you cannot solve this Hamiltonian. So if you have just a first term, it's a non-interacting, so you can solve, obtain the bond structure and so on. But once you have interaction, it becomes much more difficult. And actually, in one dimension, you can still solve this model by Bethe-Ansatz, but in 2D, 3D, you cannot solve. But we can try mean field treatment of this Hubbard interaction term. So we replace one of this electron number by its expectation value. So then this expectation value acts as a kind of chemical potential for upspin electron and downspin electron. And if you introduce the spin imbalance, that is, if you consider the different population of upspin electron and downspin electrons, then it produces different chemical potential for upspin electron and downspin electron. So spin imbalance basically acts like an effective magnetic field in this mean field type approximation. And so introducing spin imbalance is equivalent to saying the system somehow has a spontaneous magnetization M. And we can assume that there is some spontaneous magnetization M and calculate the ground state energy for given spontaneous magnetization M as assumed. So there are two parts. So one is changing the interaction energy. So the ground state energy per site in this mean field approximation. So N0 is the original density of up and down spin electrons. And when you have spin imbalance or spontaneous magnetization, the up spin population and down spin population becomes different. N0 plus N and N0 minus M. So this is a new mean field energy of interaction. And you subtract the original energy. So this gives us a difference in energy due to the spontaneous magnetization. And if you compare these two, you get minus U times spontaneous magnetization squared. So actually, if the interaction is repulsive, you can lower the energy by generating the spontaneous magnetization. So this suggests that indeed interaction can lead to the spontaneous generation of magnetization. But you have to compete with the kinetic energy. So the kinetic energy is minimized by zero spin imbalance. So if you introduce spin imbalance, upspin, the Fermi energy for upspin electrons goes up, and the Fermi energy for downspin electrons goes down. So in total, there is some energy gain. And you can compute this energy gain for kinetic energy. And the result is that this is again proportional to magnetization, spontaneous magnetization squared, but the coefficient is positive. So introducing spontaneous magnetization increases the kinetic energy as an expectation, at least in this mean field approximation. And this coefficient is 1 over density of states at the Fermi level. So if you add together, if U is small, then this kinetic term wins. So that means that M equals 0 is still the energy minimum. So the non-magnetic state is stable. But if you crank up U, at some point, D times U exceeds 1. In that case, at least within this analysis, you can lower the energy of system by cranking up spontaneous magnetization M, which suggests that actually the system original non-magnetic ground state has some instability, and there's an instability towards the formation of the spontaneous magnetization, which is nothing but ferromagnetism. And so this is called Stoner criterion, and this is already kind of suggestive. One is that this interaction U has to be sufficiently large. And also, the density of state D at EF should be also large to help realizing ferromagnetism. And in fact, I'm not going into details, but this is thought to be related to ferromagnetism in several materials like a nickel and maybe cobalt, where people found a large density of states near the Fermi level in these compounds. So in these compounds, D at EF is large, so it's relatively easy to realize this so-called Stoner criterion, which is a criterion um, for ferromagnetism, at least in the mean field type approximation. But of course, we have to question whether this is right, because this is just a result of certain crude mean field approximation. Actually, later there was more refined analysis in which this U should be replaced by some more denormalized kind of U, but let me not go into detail. But anyway, so this was result of some crude mean field theory approximation. So there is no guarantee that this is actually correct. So while this is very simple and useful and also instructive and suggestive about some ferromagnetism in real material like nickel, as often is the case with any mean field type approximation, this Stoner criterion often overestimates the ferromagnetic tendency or instability. Actually, we can find many counterexamples to this, at least naive version of Stoner criterion, because it's, oh, sorry, this was typo. So I wanted to say that, okay, so if you have a repulsive interaction Hubbard model, and, oh, no, this was okay. So if you consider repulsive Hubbard model, and so U is just a theoretical parameter. So in principle, we can imagine U goes to infinity. And if you believe this Stoner criterion, this Stoner criterion seems to suggest that for any kind of Hubbard model, if you send U to sufficiently large, then the system is always ferromagnetic. But it's not really true, because we know many counterexamples. Yeah, especially for Hubbard model at so-called half filling, that is 1 electron per site, that is on average 1/2 upspin electron per site and 1/2 downspin electron per site. So in the strong repulsion limit, so if you send U to very large value, then what happens at half filling is that each site is occupied by 1 electron, basically, because if you put 2 electrons on the same side, there is a strong Coulomb repulsion. So the ground state looks basically like each site is occupied by 1 electron. But those electrons can take upspin or downspin. And there is an effective interaction between neighboring electron spin coming from virtual state. So you can try to do some perturbation theory in U over U. So in the zeroth order, there are many degenerate states because spin states are free. But then if neighboring sites have opposite spins, then this spin can hop to the neighboring site and comes back. So this gives so-called exchange interaction, and you can evaluate the effective exchange interaction, which is t squared over u. And for any sign of t and repulsive u, this effective spin-spin interaction between nearest neighbor for half-filling Hubbard model in strong U limit is t over u, t squared over u is positive, which means that the interaction is anti-ferromagnetic. Means that actually half-filled Hubbard model in this limit is actually anti-ferromagnetic, not ferromagnetic. So this is one simple example that Stoner criterion is actually not always correct. And yeah, still we can ask why this Stoner criterion? Can we, formulate this Stoner criterion like idea in more general setting without using mean field theory? Actually, the simple mechanism or interpretation was proposed by Heisenberg. That is, we introduce a Coulomb repulsion between electrons. Then electrons want to avoid each other. But if you have a ferromagnetic spin configuration, that is spin pointing to the same direction, then two electrons cannot come to the same point because it would violate Pauli principle. So the Fermi statistics or Pauli's principle automatically, put another electron with the same spin state away from this electron. So in this sense, at least in a very intuitive way, in the presence of Coulomb repulsion, the parallel spin configuration seems to be favored. But we already have seen a counterexample, like a half-field Hubbard model. So actually, if you try to formulate this idea in precise mathematics, there are many subtleties. So this doesn't work so easily, but sometimes we can interpret the resulting ferromagnetism in terms of this kind of simple mechanism. Okay, so to demonstrate the difficulty, I want to show in simple manner that there is a kind of no-go theorem for two electrons. That is, two electrons with spin-independent interaction always has a singlet ground state. Of course, two electrons is not a many-body system, so it's not a system we really want to discuss ferromagnetism or not. It's just a two electron system, two spins. But still, we can ask whether the ground state has a non-zero spin or a spin zero. So if the ground state has a singlet uh, spin state, then it's more like a non-magnet, not ferromagnet. And the proof is kind of simple. Okay, so I'm not going to discuss precise conditions and so on. But basically, the idea is that the total wave function can be decomposed as the orbital part and spin part. And now I'm assuming that the interaction is spin independent. So basically the ground state is chosen such that the orbital wave function minimizes interaction. And for very general ground state of some Hamiltonian, very generic Hamiltonian, I'm not, yeah, there are some conditions, but I'm not going to specify details. But probably you remember that in single particle quantum mechanics you learn in undergraduate, the ground state wave function is always nodeless. So you can choose wave function to be positive everywhere. And for example, in square wave potential or harmonic potential, the ground state is always nodeless. And if you have node in the eigen state wave function, it's basically the excited state. And the same logic can be applied to two particles or many particles. So the ground state for this two particle wave function must be also nodeless and positive. So such orbital wave function must be symmetric under exchange of R1 and R2 because it's positive. But that means that since total wave function is product of orbital part and spin part, the spin part must be antisymmetric. And if you have two spin one halves and the spin wave function is anti-symmetric, then it must be singlet. So in this way, for very general spin-independent interaction Hamiltonian, actually we can see that the ground state of two electron system has always spin singlet. And this is, again, kind of counter example to naive argument that if you have repulsion, then, okay, so maybe parallel configuration has lower energy because they avoid each other. But if you really carefully analyze the equation, then at least for two electron case, we can see this conclusion easy. Okay. Then, so this shows that it's kind of difficult to realize ferromagnetism in interacting electron system. Although if you do mean field analysis, okay, Stoner criterion seems to suggest that it's easy, but it's not really easy. But there is one intriguing example where ferromagnetism was really rigorously proved, at least in some sense, in interacting electron system. And actually, it's about the Hubbard model. So it can be any other lattice, but again, let's consider the Hubbard model on cubic or square lattice, and consider the infinite repulsion limit. U goes to infinity. And a few minutes ago, I just said that this system in strong U region is actually anti-ferromagnetic because you have anti-ferromagnetic exchange interaction T square over U, which is positive. But here, I really take the limit of U goes to infinity. Then this J goes to 0. So the system was anti-ferromagnetic at half filling, but this exchange interaction goes to 0. So it's more like each site is occupied by spinful electron, but the spin state is completely free. So it's more like a parameter. So this is, of course, so at half filling and U equals to infinity, this is just a collection of free spins at each side. So this is, of course, not ferromagnet. But, so this Nagaoka proposed that, okay, let's remove one electron, or equivalent to you dope single hole into the system. Then this single hole can move around the system. And remarkably, he proved that such a system with a single hole, just single hole added to half-filled Hubbard model is indeed ferromagnetic, which is kind of surprising because at a zero hole doping for finite U, it's anti-ferromagnetic. But once you take U to infinity, there is no magnetism, but then you dope single hole, then the ground state is ferromagnetic. That's very surprising, but this is a rigorous result proved by Nagaoka. And the original proof was kind of involved, but later there was a simplified proof provided by Harutasaki, who is a T of AKLT model in spin chain business. And according to his paper, yeah, basically you can prove this Nagaoka ferromagnetism using so-called Perron-Frobenius theorem. So because so in this system, U equal to infinity, each site can be occupied by either up spin electron or down spin electron or a hole. And you can only move this single hole around. So if you remember so-called 15 puzzle, so you have 4 by 4 squares and 15 panels with numbers, the one hole, and you can only move this hole around and shuffle these numbers around. You want to reorder this number from 1 to 15. And in this limit, the Hubbard model is like this 15 puzzle. So you can move hole around, which shuffles a spin pattern. But he pointed out that all the spin states can be connected by sufficient number of this single hole motion. And also, you can choose a phase factor such that the matrix element of this whole motion between one configuration and the other configuration is always negative or 0. So in that case, so-called Perron-Frobenius matrix theorem implies that the ground state for this Hamiltonian is unique for given total SC. And also the wave function again has an all positive coefficient. And the all positive coefficient means it's symmetric under exchange of spins, which implies that total spin must have a maximum value, which is nothing but ferromagnetism. So in this way, mathematically, you can prove surprisingly the ferromagnetism in this single hole doped case. So I'm running out of time, but let me just mention briefly about Perron-Frobenius theorem. So I'm not going to show the proof. If you are interested, you can look up Wikipedia or whatever. But this theorem has surprisingly many applications. So basically, this is about positive matrix or non-negative matrix. That means that all the matrix elements are positive or non-negative. Then this often happen in stochastic process, because in stochastic process, we often consider transition matrix. That is, you have bunch of states, and if you are in certain state, J, you can transition to different states. And generally, you can think of the set of probability Tij, which gives a transition probability from state J to state I. So if it's Markov process, this matrix T specifies stochastic process. And if you start from some initial probability distribution P0, and if you do this process n times, then after that, probability distribution is given by matrix T to the power n applied to the initial probability distribution vector. So if you consider asymptotic limit n goes to infinity, then T to the power n is dominated by largest eigenvalue. So the largest eigenvalue of T and the corresponding eigenvector actually gives you the steady state, which you can reach by repeating this stochastic process very, very, very long time. And this Perron-Frobenius theorem guarantees that under certain conditions, the steady state is unique. Whatever initial state you choose, if you repeat this stochastic process, you converge into the same steady state. That's guaranteed by Perron-Frobenius theorem. And actually, this has a very famous application if you know about this. So this is a paper. So this is maybe one of the most cited papers in the world, not in physics, but in computer science, written by two guys from Stanford, Sergey Brin and Larry Page. Of course, they founded Google. And this is a basic principle, at least of original Google search engine. Okay. I think now it's much more complicated, but this was the original idea. So they wanted to obtain, they wanted to define page rank, which, quantifies the importance of each web page in the world. And to define the page rank, they introduced some fictitious stochastic process, like a random web server, which start from some random web page, but follow the link. And every time you find several links, and then randomly pick one of the links and jump to the next page and repeat. And if you tweak this stochastic process a little bit, you are guaranteed to converge a certain probability distribution. And the page rank importance of this page is nothing but the probability you can reach certain page in the steady state distribution, actually, which corresponds to the largest eigenvalue, eigenvector of this transition matrix. So this is nothing but the Perron-Frobenius vector. So we could say this is application of Perron-Frobenius kind of theorem, although in their paper, they didn't mention any Perron-Frobenius. So you can find the important thing even without knowing formal mathematics if you work on important, interesting problem, which also happens in physics. But if you want to generalize and so on, optimize, of course, precise mathematics can help you. So this is one interesting application of Perron-Frobenius theorem in computer science, but in physics, it can be used to prove the Nagaoka ferromagnetism and several other interesting results. So let me stop here for today. Thank you.
Because typically the pure accidental picture, I think about density states, and then you multiply it into head, right? But it actually real experiment. For example, nickel, if you do experiment, you'll find it's really sort of like a local movement type of picture, right? The scattering has to be sort of really follows the nickel local movement profile. How do you actually understand that?
Yeah, that's, I don't know. Yeah. So that's, yeah, I think, yeah, that's a really important question. I want to answer, but I don't know the answer. Yeah, so this is very crude approximation and not quite real space picture, I agree, but yeah, 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 yeah. Yeah. So maybe there is a way to start from more localized picture, but yeah, maybe he has better answer.
In a way, this is already indicated by this criteria.
Mhm.
Formulation that the core interaction has to be non-perturbing.
Mhm.
So if this dimensionless interaction is larger than one, what the constraint is saying, in some sense, the count is reflecting some non-perturbing physics.
Mhm.
Real.
Yeah. So wait, yeah. So of course this doesn't really, give quantitative picture of anything, and often even fail qualitatively. So I think we want a more general picture, taking the interaction from the beginning, some sort of non-perturbative picture. I agree, but I don't know how to do this generally.